Welcome back to another explainer. Today, we're skipping the code and logic gates. Instead, we're shining a massive spotlight on a hardworking, totally silent hero of the electrical world, the current transformer, or simply the CT. Picture this. You want to measure the speed of a rushing, raging river. You wouldn't just stick your hand right into the current, right? The sheer physical force would absolutely snap your wrist. Well, high-voltage systems are exactly like that river. Hooking a delicate standard ammeter directly to a 1,000-amp line? Yeah, no way. It wouldn't just break, it would literally vaporize. So here's our roadmap for today's explainer. We'll cover the high voltage problem, the anatomy of a CT, how the magic actually works, a palette of CTs, and finally, bridging the mega and micro. Okay, let's dive right into part one, the high voltage problem and why we desperately need a translator. So the core issue here is measuring a totally destructive force without blowing up our gear. The elegant fix? The CT acts as a crucial translator. It grabs those massive, untamed currents and purposefully shrinks them down to a safe, bite-sized scale that our instruments can actually handle. It fluently speaks the language of both raw, heavy-duty power and delicate electronics. Moving right along to Section 2, Anatomy of a CT. Let's deconstruct this silent hero. Now, a CT might just look like a heavy hunk of metal from the outside, but it's a super precise instrument built from three main parts. First up, the primary winding. This connects right into the main circuit. Actually, in a lot of industrial setups, this isn't even a separate wire. It's just the main conductor itself, like a thick bus bar passing straight through a hole in the middle. Pretty cool, right? Second, the magnetic core. This is usually laminated silicon steel or permalloy, giving the magnetic flux a dedicated path to travel. And third, the secondary winding. Think of this as a coil of superfine wire tightly wrapped around that core. This is exactly where that safe, shrunken current gets produced. All right, Section 3, how the magic works. Time for Faraday's Law in action. We know the hardware, so let's get into the physics. The whole operation relies on a foundational scientific theory, Faraday's Law of electromagnetic induction. If you remember this principle, it explains how a changing magnetic field can magically induce an electrical current in a nearby conductor, without them ever physically touching. Sounds like a magic trick, but it is pure elegant physics. So here is the step-by-step breakdown. Step 1, the flow. AC, alternating current, flows through that primary conductor. Step 2, the field. Because it's AC, that shifting flow creates a wild, constantly varying magnetic field around the conductor. Step 3, the core. Our trusty laminated core catches that wild field and neatly wrangles it, directing it right through the secondary winding. And finally, step 4, the induction. That changing magnetic field spinning through the core induces a brand new, perfectly proportional current right in the secondary. Now, what's really interesting here is the math, specifically the transformation ratio. This is where the actual translation happens. Imagine your primary has just one turn, like that main cable passing straight through the hole. Now say your secondary coil has 100 turns of fine wire. Mathematically, a huge 100-amp current in the primary shrinks all the way down to a perfectly safe 1 amp in the secondary. All that heavy lifting, done purely by the math of those turns. Okay, hold up. Before we go any further, I absolutely need to hammer home a critical safety note. Listen up. You must never, ever leave a CT secondary open-circuited while the primary is energized. Seriously, why is this a literal life or death rule? Well, if you don't give that secondary current a path to flow, the physics turn violently against you. The voltage across those secondary terminals won't just sit there quietly. No, it will massively spike to thousands of volts. We're talking instant insulation failure and, honestly, a very real risk of a lethal shock to anyone nearby. It's absolutely crucial to remember this. Okay, moving safely along to Section 4, a palette of CTs, or tools for every job. You know, you wouldn't use a sledgehammer to drive a tiny screw, right? Same goes for CTs. There are variations built for highly specific environments. We've got indoor and outdoor models, which just depends on their insulation. Think resin casts for inside and tough porcelain or polymer for outside. Then there's the bar type, featuring a solid bar built right in as the primary. You also have window or ring types, where you just slide your cables straight through the open center. But man, my absolute favorite has to be the split core design. It is brilliant. It literally snaps open and shut like a clamshell. You can just lock it around live existing cables for retrofitting, no need to shut down or disconnect the main circuit. A real game changer. Now, these different physical builds really come down to two main jobs: metering and protection. This brilliantly illustrates the difference. Metering CTs are built for high accuracy at normal, everyday loads. But if there's a huge surge, they're designed to saturate, basically hit a wall and stop increasing output. Why? To protect the delicate, expensive meters attached to them. Protection CTs, on the flip side, are the heavy-duty bodyguards. They stay highly accurate even during massive electrical faults or short circuits. Their whole job is to scream at the protection relay, telling it exactly how massive a fault is, so it can immediately trip the breaker and save the whole shebang. Which brings us to our final stop, Section 5, Bridging Mega and Micro, and why this all matters. Let's zoom out to the big picture. We've talked a lot about the guts of the machine, but without the CT, our modern infrastructure, it just wouldn't work. These unseen little devices let us safely monitor entire power grids. They are quite literally the reason power companies can accurately bill millions of homes and businesses. Plus, they're the essential guardians protecting massively expensive industrial motors from burning up when things go sideways. So, the crucial point is this. The CT is the ultimate bridge. It takes the mega world, raw, high voltage, totally untamed power, and safely tethers it to the micro world of super precise control systems and delicate analytics. It makes the impossible to manage completely manageable. Which leaves us with this final thought. Next time you flip a light switch or see a massive factory roar to life, ask yourself, what invisible translators are silently protecting the power grid right now? It's kind of wild to think about the unseen physics making our modern world tick. Thanks so much for joining me for this explainer. Keep digging into those systems, and I'll see you next time.